Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. Thank you for coming to the MSR Colloquium. It's my job to introduce Joel Spencer. I don't know what to say. There's so many people in this room who know Joel well. I'm just going to start with a personal reminiscence. So 2003 summer, I've just started an internship at Microsoft Research. It's my first ever experience with this group. 1 or 2 weeks into the internship, Joel visits and just drops by my office one day and says, "Hi, I'm Joel Spencer. Do you want to chat?" And my jaw dropped. I, of course, knew of him. His book on the probabilistic method is a Bible for me and anyone else in my generation who developed an interest in discrete math. And I was so flabbergasted that this famous mathematician would want to come in and talk to me. We had a fantastic conversation. It's been fantastic talking to him every time he visited the lab. Since then, when I was around, we love to have Joel visit, and I hope that you'll keep coming back many, many times in the years to come.
Great. Thank you. Thank you.
So in fact, Joel just promised me he'll visit for some time in the fall.
Yes. 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 So the Galton-Watson process is a very vital mathematical process, but it was certainly controversial for its sociology right from the beginning. Some of you may know Peter Jägers, who's a distinguished statistician at Gutenberg, and also fairly political, and he actually looked into a lot of the history. In this talk, we'll just talk about the mathematics, but Galton and Watson, here they are, looking appropriate for their age. And I was talking to Mary Gray about this to get the sociologist's perspective. And we came to an agreement that the word misogyny would not accurately reflect Galton and Watson, because in the Galton-Watson process, there are no females whatsoever. So one has to invent a new sociological term for a society not that's against females, but has a total absence of maybe it was called Cambridge at the time. A good name. So it has an interesting and controversial history, but it certainly is some beautiful mathematics. Now, the Galton-Watson process can be over any distribution, but I'm going to be talking about the Poisson distribution because here's the formal definition. But the real key thing that makes the Poisson nice, so since this was Galton and Watson, I changed Adam to Eve, you might notice, that if you have Poisson mean lambda children, and each child is of type J with probability P sub J, then that's the same thing, not asymptotically, that's exactly the same thing as saying that the number of children of type J is Poisson with mean P sub J lambda, and that those number of children is independent. So if you're going to have Poisson 5 children, and each one is male or female with probability 0.5, then that's exactly the same as having Poisson 2.5 male children and Poisson 2.5 female children. And that property plays a nice role, although we want to look at other distributions, which is work in progress. And here I should make sure I add that this is with my graduate student, Mumanti Potter at the Courant Institute. And time for an advertisement. So thank you for the kind words about the probabilistic method, but please throw out your old copy because all the really good stuff is in the 4th edition. And it's coming out any day now, any day now. They said December, so We're all excited about it. And
Did you choose red and green on this slide because you want people to consider it as a stocking stuffer?
yeah, that was a deliberate choice. That's right. Yeah. Okay. So this is the Galton-Watson process, which many of you are familiar with. That the Eve has Poisson mean lambda children, and then all its children have children with the same distribution. Then you have grandchildren and great-grandchildren. And it may go on forever or it may be finite, and that distinction becomes quite important. Okay. And in analyzing things, this is something I like as a general thing in analyzing random structures. I like to pre-process the randomness. And this I like to call fictitious continuation. So just thought about the way to analyze it. You let x sub I be, your probability space is that x sub I is Poisson lambda, mutually independent for all positive integers I. And then you say that the ith node has x sub I children. So for example, if you have the following string, then Eve has 2 children, Anna has no children, Barbara has 1 child, Carol has no children, and at that point the process stopped. There are no more children, but the fictitious continuation is that it continues with Danielle having 3 children, Florence, Gabriel, Harriet. That didn't actually happen, but this is very helpful for the analysis. And as a general point about random structures, I find that analyzing random structures, and we had this conversation, that it's very helpful to pre-process the randomness in some way. Otherwise, you get into all sorts of problems about conditioning on the past, and this helps to avoid it. So just a general comment about that. All right, let's take an example of a property that some node has exactly 1 child with 1 child. Maybe we can call this the old China property, since China has now changed its policy, but this is so let's call this the old China policy. And how do we analyze it? Well, the way I want to do it is I want to have a finite phase space, green for yes, red for no, and yellow, well, we'll see. And when I count, I'm only going to count 0, 1, and omega, where omega stands for any number bigger than or equal to 2. And I'm going to call a node green if, when you look at that node and downward, that is the tree generated by that node. Of course, trees have this recursive nature, which is so central. When you look at the node and go downward, that there will be some node in that tree that has exactly 1 child with exactly 1 child. So then you call the node green. I'll call the node yellow. Is a kind of an intermediate step. So V is labeled yellow if V has exactly 1 child, but it's not labeled green. And otherwise, it's labeled red. And now what I want to say is that if you want the state of a node, you just look at the states of its children. And the states of its children determine the states of its node. And furthermore, in counting how many green, yellow, and red you have, you don't have to count past 1. The counts are either 0, 1, or omega. So it doesn't matter whether you have 6 yellows or 11 yellows. That's counted as the same. And you can determine the rules. So just briefly, if you have a green child, then you're definitely green. And in fact, if you have many green children, you're definitely green. But what happens is, if you have exactly 1 child, which is yellow, but that point had exactly 1 child, so that means you're green. And if you had exactly 1 node, which was red, then you're yellow because you have exactly 1 child. And otherwise, you're red. I mean, you can work them all out, okay? Lotsie. Exactly 1 child.
No, green means your subtree satisfies the...
Oh, so the state of a node is you look at the tree starting from that node, going down, yeah. So you have some tree For each vertex, in the tree, I'm going to give it red, yellow, or green, but I'm going to just look at the subtree generated by it. And these are the rules. I'll call it green, yellow, or red in these three cases. And now what we do,
why is the last one green? Because it has 0 childs.
that's yellow.
No, but it has 0 childs.
No, it has one child. It has one red. It has 0 green children, 0 yellow children, and 1 red child.
It just counts the children. It's not a sequence. I should.
Right. Yeah. These are in order. That's why they're color coded. Yeah. This means 0 green children, 0 yellow children, and 1 red child. Then you're yellow. You're not green, but you are yellow because you've had just 1 child. So, all right. I mean, you look at this and you come up with these rules. Once you have this situation, which we're going to generalize, then you can get a system of equations. You let x, y, and z be the probability that the random tree is going to have its root. The state of a tree is the state of its root node, is going to be yellow, green, yellow, or red. So you really have just 2 variables because it's a distribution, 2 independent variables. And what you see is you get some equations. The probability of being green is, well, let's do yellow. The only way to be yellow is if you have 0 green, 0 yellow, and 1 red. But remember, the number of green is Poisson lambda x. And the number of yellow is Poisson lambda y, and the number of red is Poisson lambda z. So the chance that you have 0 green is e to the minus lambda x. The probability of having 0 yellow is e to the minus lambda y. And the probability of having 1 red is lambda z e to the minus lambda z. When you do the mathematics, you get this equation. For x, it's a little bit more complicated because you have all these things. But you get an equation for the distribution in terms of the distribution. Okay. And it turns out, I mean, this was one of our early examples, that you can now solve this, and you get a nice solution. It's implicit, but still, it's a solution, and you get a unique solution, which is going to be really important. And here's actually the graph, although this is the probability. This is 1 minus. So this is the probability that you have no node that has exactly 1 child with exactly 1 child. And we can get this analytically from the solution to the previous equations. Which, I mean, so it takes some analysis, but we're all good at math here, so we can do that. Well, my grad student said it had that solution. Okay. Now, let's look at immortality, which is the classic thing that Galton and Watson were so upset with the possibility that the noble classes were going to disappear. So that was their objective of study. And this is really classical stuff. Now there's just 2 states, yes and no, and the count is either 0 or non-zero. So many is 1 or more. And now if you have any green children, you're green, but any is many. I mean, because omega is 1 or more. So if you have any green children, you're green. So if you have a node that has, if you have, let's get biblical about this. If you have Cain, and Cain has an infinite number of children, then Adam has an infinite number of children. I would do it with Eve, but I don't know about the female. The female children seem to have disappeared from the Bible. So an infinite number of descendants, exactly right. Infinite number of descendants. Yeah, what were the daughters of Adam and Eve? Maybe they didn't have any. It was mystery.
One of the sons had a child with the mother.
It must be the solution. I think that's the only possible solution I could come up, at least. But I don't know. I fail to knock. So what can I tell you?
You know the movie with the Wind?
Yes, yeah, the monkey trials, yeah.
Clarence Darrow makes a great speech in that movie about Kane's wife and where the heck did she come from.
I knew I wasn't clever enough to think of it myself.
Creation in the next county is.
Okay, so here, this is very classical stuff. You get an equation. I mean, you only have one variable because if the distribution's on 2 points, it's a distribution, so there's only one variable. X, and you get this classical equation, x equals 1 minus e to the minus x lambda. But something funny happens here. There are two solutions to this equation. There are two solutions to this equation. And here they are. I mean, when lambda is less than 1, the only solution is 0. So again, there's some nice stuff for a good first-year calculus student to do this. And you find that for lambda greater than 1, there are two solutions. One is 0, which means that the process the probability of immortality is 0, so the noble families are doomed. And the other is this positive number. And one can prove in this particular case that the correct answer is the positive number. Again, this is classical stuff. And really today I want to say, let's not look at this as some anomaly, but let's look at the question, when you get these systems of equations, when do you have just one solution, and when do you have several solutions? And if you have several solutions, which is the actual answer to the question that you're looking at? So let me give another example. I have to thank my daughter for coming up with the title of it. So let's imagine so maybe this is the Korean.
Sounds like.
Yeah, right. Maybe this is the Korean method, because I just read an article that this is South Korea, actually, that South Korea is very upset that their birth rate is now 1.2. Well, of course, now we have two genders, but in this model, it would be 0.6. Okay, and they're trying to do something about it. Well, one suggestion would be Draconian fecundity, which is that if you only have 0 or 1 child, you're killed. Okay, I mean, this was Yael's mode, but she. But it turns out that having 3 may not be sufficient, because what? Yeah, just give. I am not pointing at you for any reason. Because what happens is, if your children don't have enough children, then they get killed, and if you're left with less than 0 or 1 living children, then you're killed. All right, so this is the model, yeah.
The word logic is in the title of your talk, so I thought you were going to be limiting yourself to first-order properties.
I'm not limiting myself, but I will be talking specific. Okay. Yeah, these are not, but that's right. So right now I'm looking at several properties. I will be specifically talking about first order, but I won't be limiting myself to first order, but good point. So here, another way, we don't have to put Yael on the data here. We could say that the property is that the tree contains in it an infinite binary tree. There's a subset where the root has 2 children, both of which have 2 children, erasing the other children, both of which have 2 children, and so on forever. And that's the same thing. All right, that's the same thing. So we don't have to do it by cutting things off. But anyway, when you do this, you get the same thing. Again, yes or no. Now the count is 0, 1, or omega. If you have, and green is yes, no, red is no. If you have omega, meaning at least 2 green children, then you're green. And if you have 1 or 0, then you're red. Okay. It doesn't matter how many red children you have, because they're going to get killed, so they won't count. So we get this set, and we get x, and we get this nice equation for x, and now we do some beautiful calculus and really great stuff. I mean, you know, when I say it's great for a first-year student, what that really means is try it yourself. It's really fun thing to try and analyze what this equation has. And now to say the special buzzword, I didn't just say this because Christian and Jennifer are in the audience, but what we get is a first-order phase transition. Yes, here it is. When we look at the solutions, we always, to this equation, we always have the solution 0, but when we reach a critical point, which is it can be given an exact value, what happens is past the critical point, we get two other solutions. And it turns out that the actual answer, the actual probability is the green line until you get to the critical point, and then, what color is that supposed to be? I don't know. Oh, no, this is the purple line, and then the green line, yeah. And that turns out to be the actual thing, but you don't see it from the analysis. You don't see it. So these are the three examples. In one, everything is not only continuous, but it's all the derivatives are continuous. In the case of being infinite, you have two solutions, and the actual answer is, while it's continuous, it's non-differentiable. And in Draconian fecundity, once you get past this critical, lambda critical, you have three solutions, and then the actual answer is discontinuous at the critical point. So, I mean, that's really an important thing when you have, when you're going to have which one. Okay. All right. Now, you asked for the first order world, so now so I want to look now at properties involving the first order world. In the first order world, you can only talk about nodes, and you can use universal or existential quantification over nodes, but only nodes. You can't use quantification over sets. And your sentences have to be finite sentences. So I think this one is that, so, pi is the parent relationship, that x's child is y and z's child is y. Yeah, and furthermore, when you want to say exactly one, you can always put exactly one into the first order system. So this is the example of the China, old China one can be written in first order. And a key thing in first order is what's called the quantifier depth, which is you have these existential quantifiers and you look at how much they're nested. So if you say for all x there exists y and for all z there exists w, that's only a nesting of 2. So the quantifier depth is how deep the nesting goes. And that turns out to be a key variable in studying the first order world.
This is not the number of alternations of quantifiers?
No, it's not. That's a very good point. And in fact, the alternations are something we're studying. So it's just the nesting. So if you say for all x, for all y, for all z, for all w, followed by a Boolean thing, that's a nesting of 4. Yeah. So what happens is,
for all. Then you have some expression which involves later another for all. Exists.
yeah, then it would be, you'd add them all up, yeah.
So then the nesting it's a total number of quantifiers,
Yeah,
not
yeah,
those
yeah.
appearing directly behind each other.
They don't have to appear directly, but they have to be inside what's called the scope. In other words, if you imagine when you say for all x, you'd add a big parentheses that came after it, then, yeah, so it doesn't have to appear directly after it, but it has to be.
Can we do away with Christian's question by just putting all first order sentences in normal form? Where
We could, but I'd rather, you could do, I mean, there's a lot of tricks to
Will it matter for us, like, as long as it's a constant, does it matter for us?
Sorry?
Will it matter for us exactly how we count it, or like up to factor 2, so etc.? It wouldn't.
No, I'm doing it with the quantifier depth is a standard thing. So yeah, it's not consecutive, but it's inside the nesting. You know that So, for all x, blah, 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 there exists y, but the exists y depends on the x, then, yeah. Okay. So it turns out that, so this is, again, some standard stuff, that if you fix the quantifier depth, there is only a finite number of first-order statements. And this is not at all obvious because you can write statements of arbitrary length, but up to tautology, there are only a finite number of statements. And this is a deep theorem, and the number is actually a Tower function of k. So it takes some doing, but let me just state that. Now, what happens is that in the first-order world, locality plays a key thing. Let me define the radius RAD to be 4 to the k, though that's not that could be a little bit lower, but it doesn't matter. Let me define it 4 to k. And now if you look at a point in the tree, you look at its ball of radius 4 to the k, and that structure, even though there are an infinite number of possible such structures, because there's no limit on the number of children, there are only a finite number of types. So k is fixed, so there are only so this finiteness is rather critical, that they fall into a finite number of types.
Type here doesn't mean isomorphism type.
Oh, type means they're the
which depth k sentences.
Exactly. Yeah. So let me repeat what Bobby said. Two things are the same type if they satisfy exactly the same depth k sentences. Exactly the same depth k sentences. And the very strong basic result is there are only a finite number of types, which follows from the fact that up to tautology, there are only a finite number of sentences. But all of that, I'm not going to give the proof of that, but it's and now what happens is, yeah.
There's something I'm maybe not understanding.
Yeah.
To say that a ball of a given radius satisfies a sentence is
Yeah.
different from saying that the entire tree.
Right. I'm just looking at the ball. Yeah.
Okay. So you're.
Actually, to be technical, I'm looking at the ball with the center as a designated point, which I left out. But
Okay. But so the sentence.
Well, you look at.
Pertain to leaves of the ball.
Yes.
And
Yeah,
this
that's
tree
right.
might actually change when you consider.
Right.
The ball
Yeah, that's true.
You don't mind that.
I don't mind that. All of that's true. Yeah, all of that's true. And now what happens is
Count only downwards, but also
upward too. No, up, downward, and upward. And it's important that it be downward and upward. And now what happens is that suppose you want the tree and you want to know what class is it in. This theorem says that under these conditions, let me come back to it, all you have to do is look at the ball around the root. Now, what are the conditions? The conditions are that pretty much any local event does occur. But it's a little bit technical, but so there's some technical things here that basically, and not only does it occur, it occurs k times, so some technical things. That is, if you think of the types of the balls, suppose that a tree, suppose you know that every type does occur, in fact it occurs k times, then the only thing that determines the type of the whole tree is what's happening near the root. See, the root might have 2 children or 3 children, and then it would be different. So you can't say that you totally know things just from the types, from the neighborhoods. Yeah. Yeah. Yeah.
When you talk about ball, what is your metric space?
Oh, yeah, 2 points are at distance 1. If they're in a parent, it's not directed. The points are the nodes of the tree. Yeah, the nodes of the tree. And so you leave out the direction. You define a graph by saying x and y are adjacent if x is the parent of y or y is the parent of x. So then the ball, so the ball of radius 4 includes the cousins. Okay, so that's, we have that. Yeah, these are good questions. And so with some technical things, what happens with the locality is that if the tree has the property that every type appears in the tree lots of times, then the type of the tree only depends on the root. And sort of it has to, like I said, it has to depend on the root. Because if the root, one tree has 2 children, because the root is a designated point. So you can make the statement that the root has exactly 2 children. So, but that's all you can do once you have the locality. So we're going to have that. And when we put this together, what we get is universality that is, again, depending on k, there's some fixed tree, let me call it some fixed tree, so that if you take, let me not call it T, I'll call it U. All right, so that if you have any tree, and somewhere in it it's got this universal thing, then its type only depends on what's near the root. Only depends on what's near. And the reason is that this universal tree already has inside it, it's like I call it the Christmas tree theorem, because the universal tree is designed to have every ball of radius r inside the universal tree, and yet it's still finite. Now let me switch to try and generalize for a moment. The examples we've had before, and this is something called tree automata that's been studied before, but not, as far as I can see, with respect to probability. So this is just meant to generalize the 3 examples we've had before. We have a finite state space, sigma. We have a set of accepted states. So this is following the theory of finite state automata, if you're familiar with that. And the key thing is that the state of a vertex means it's really the state of the tree rooted at that vertex. And there's a constant k, so that everything that's k or above is regarded as the same number, as many. And then the key thing is that in a tree automata, and so the previous things were examples, the state of a node is determined by how many of its children are of each state. And where by number I mean k or more counts as the same. And then we call the process recursive if it holds, if and only if the root has one of the accepted states. So the 3 examples I've given are examples of recursive properties. As you can define a finite state space, you can define this k, so this notion of many, so that the state, and then you, in our case, is accepted was just green. It doesn't have to be, and you have this.
So Joel, when
Yeah.
you define these Watson trees,
Yeah.
they're defined with respect to a particular sigma upmerger, defined by cylinder events or something like that.
Yes. Yeah.
So why is it clear that your finite state space is in that sigma?
It's not clear. No, it's not clear. I'm going to say, suppose you have a finite state space, and then go on. Yeah. I'm going to look at examples where you do have a representation by finite. I mean, you could make up other properties that don't. But these are, in fact, I'm going to restrict really to that. Yeah. So. And a theorem, which is a nice theorem in logic, is that if you have a first-order statement, that these are recursive. And the state space is the possible Ehrenfeucht classes. And there's a proof involving the Ehrenfeucht game, but let me not, that would take me too far down another road. So let me just state this as a result that if you have a node and you look at its children, and each child generates its own tree, and this tree has a state, namely its state is its, 2 things have the same state if they have the same truth value on all quantifier depth k statements. And so there's only a finite number of states. If you know the states, Maybe this one doesn't have any children. Maybe this one has the same one as this. And maybe this. If you know for each of the children of the node what the state is, and furthermore, the numbering is such that if they're more than k of a particular state, you don't care that you just know that they're more than k, it doesn't matter. Then from that, one can deduce, so I'll just state this, one can deduce the state of the whole tree. So this is a nice logic theorem, and the proof proof we have uses Ehrenfeucht games, but it would take some getting into. Okay. What happens is, though, that first order is not the only thing. If we look at monadic second order properties, these are also recursive. Now, what does monadic second order mean? In monadic second order, you are allowed to quantify over sets of vertices. So again, you have universal and existential quantification, but you're allowed to say there exists a set S. So if you want to say that the tree is infinite, you can say there exists a set S, the root is in the set S, and for every x in S, there's a y in S which is a child of x. And sorry?
You can say that there are two kids and then you get the property that you mentioned before.
Exactly, exactly. So all these examples that we've had have been monadic second order. And so there's a nice connection that the monadic second order properties are recursive properties. In fact, it goes the other way. So we have this nice connection between the logic of what's called monadic second order logic and these recursive properties, which are more combinatorial in nature. Now,
Is the converse also true, by the way?
yeah, it is.
Recursive properties are
Yes, yes, yeah, it is. Yeah. Yes.
Is this restricted to trees, or could I formulate that for an arbitrary graph?
You could look at arbitrary graphs, but I'm not sure what the results would be. I don't know. We've just looked at it. Trees have this nice recursive property that you have a root node, and then each child forms a tree, and they're disjoint from each other. And that seems to be central. But I don't know. Maybe there are other ways to do it. I don't. I'm restricting to trees, okay? It's a good question, but the answer is...
I might want to know whether I have some graph, does it have an infinite component?
Absolutely, absolutely, yeah. And I don't know the answer to that. I'm restricting to trees here, yeah. Yeah, no, good question. I don't know. Okay, so when we get these equations, we're going to get a solution which may be regarded, since we have all these economists around here, as a fixed point. So how do we do that? We look at the set of distributions, just maybe not so many.
No, we do have a few.
Yeah. So what do we mean by a fixed point?
But other people use fixed point. Well, anyway.
That's true. That's true. That's true. So we're looking at the set of distributions. Now this is a finite dimensional space. So we're looking at this. So this is a nice compact set, the set of distributions over the finite set. And I want to map distributions to distributions. So I'll just say this. Take a point V. Let it have Poisson mean lambda children. Give each of those children a state with the distribution x. Those states then, which is because of Poisson, we can do it in this nice way in terms of calculation. And the states of the children then determine the state of V, and so that defines a distribution on V. So the distribution on the children defines the distribution on the parent, and so we have a map from distributions to distributions. If we have a distribution over the states of the children, then we have a distribution on the parent. And what we're looking for is the fixed point. That's the equation that we've had can be expressed. I mean, we did it with variables x and y, but now we're just using vectors. This is just the fixed point of this map psi sub lambda. Well, we're able to get a lot of theorems here that I'll be able to state. One is we can show that psi sub lambda is a contracting map on the set of distributions. So in particular, that means it has a unique fixed point. It has a unique fixed point. But this is when A is after when A is not a first order property, we have examples where there's more than one solution. We've had examples where there were 2 solutions and 3 solutions. But when it's first order, we have a contracting map, and that means that the fixed point is unique. And furthermore, this is the result I like best, is that when you look at the probability of a first order event in the Poisson tree, and you look at it as a function of lambda, it's real analytic. Everything is nice about it. All of its derivatives exist. Okay, so I mean, we've seen 3 examples. One that was real analytic, the second which was non-differentiable at the critical point, and the third one, the first order, was non-continuous at the critical point. But what this says is that if you have a first order property, then none of those bad things happen. And indeed, as a function of lambda, it's a real analytic function. It's given implicitly as the solution to these equations rather than explicitly, but still it's a well-defined function. A further thing is that if you condition on the tree being infinite, then things are particularly nice, because whatever statement A you have, it only depends on another statement, call it A tilde, that involves the neighborhood of the root. And that follows from those general statements. I won't go into the technical stuff about it, but I want to give this definition, which I think I like very much. So the T sub lambda are given by this fictitious continuation. And there's a nice notation by Don Knuth that never really caught on. Many of his did. But this one didn't, and I think it should, especially for people nowadays. Let's call something quite surely if its failure probability drops exponentially. And he actually put this out generations ago, and it never caught on. But I think nowadays we're very often thinking about things that happen quite surely. Well, there has to be there has to be an index. There has to be an index here. You have some kind of index, and you say that something occurs quite surely in the index S if the probability that it doesn't occur is dropping exponentially in S. And as we now, I think most of us have dealt with things that occur quite surely. So I'd like to resurrect this notation. And now the following thing, I want to call a properly rapidly determined if quite surely the first S values tautologically determine whether the statement is true. There's an interesting combination here. It's quite surely, absolutely surely determined. I'm not saying it's absolutely surely true or false, but it's absolutely surely. So
seems similar to probably approximately correct.
yes, maybe that was in the back of my mind. I don't know.
Probably exactly correct.
Right. Yes. That's it. Yeah, that would be that. That's right. So we call something rapidly determined if it has this property, and what happens is that the first order A are rapidly determined, which I think is interesting in its own right. And just to quickly go through.
For non-computer
Wait, sorry, let me get back first here.
So why, in your example with the Draconian fecundity, why was that not a first-order property?
Sorry, say again.
So you showed an example with Draconian fecundity, right?
Yeah.
And why was that not a first-order property? intuitive?
Well, it's just not. I mean, I can prove it's not, but the statement of it was that there exists a set where everything has two children. So you're saying there exists a set. In first order, you're only allowed to say there exists a vertex. So the way you'd like to say it is there exists a set of vertices in which each node has two children. But in first order, you're not allowed to say there exists a set. Okay? Is that? Yeah. And one can actually prove that it can't be done in first order. As a matter of fact, one proof that it can't be done is from this theorem, because we proved that the function is nice, and this one doesn't have a nice proof, a nice function. So what we can actually show is that the first order are rapidly determined, but let me skip over some of the technical things here because I want to finish up with some things on second order. So what one can show through some technical things is that in the first order, one gets a contraction map, and it takes some, but it's based on the locality, but still, as you can see, it's not a 1 minute argument, but there's some stuff. So let me jump ahead to what happens if you condition on the tree being infinite. And now there's a very nice theory that Mumanti has worked out in great detail, which is that if you ask for what is the almost sure theory, that is, what can you say about the statements that hold with probability 1 conditioning on the tree being infinite? Well, for each tree, for every tree with probability 1, that tree is a subtree. If the tree is going to be, if we know it's infinite, it's not too hard to prove, but I mean, it takes proof, but it's not too hard to prove that conditioning on the tree being infinite, if you take any particular finite tree, it's going to show up somewhere. I mean, it takes proof, but it's true. And it turns out that schema is enough to get the almost sure theory. That is, if you take those as your axioms, then one can show that every statement that holds with probability 1 follows from those statements. So we have a good feeling for the almost sure theory. Furthermore, if we look at any statement at all, if we look at the almost sure theory, and if we add what the nature is of near the root, then we will get something that's, well, it's K complete. There's any first order statement of quantifier depth K is either true or false. And so from this, one can further deduce that for any statement A of quantifier depth K, even though the statement A is talking about all sorts of stuff, but it's first order, the probability of A is just determined by these various probabilities that only depend on looking near the root. And these probabilities turn out to be nice, but you can read Mumanti's thesis when and if she writes it. I mean, in fact, actually, there's something on the archives already that giving more what nice means. So what happens is, for any first order statement, the probability of A, given that the tree is infinite, is a particularly nice function of lambda. It only involves exponentials and polynomials and nice stuff. Okay. Let me just at the end go, yeah. Yeah.
So in particular, it's real analytic.
Sorry?
So these conditional probabilities conditioned on immortality also turn out to be real analytic.
I mean, that's, I guess, a
Yes,
proof,
yeah.
Is that like a proof of the previous theorem? Or?
No, because the previous theorem is not conditioning on immortality, and when you condition on finiteness, no, you need more. Yeah. Let me turn to the monadic second order, and there's several different things going on which I feel combine the logic and different elements. So monadic second order is you're quantifying over sets of vertices. So you can say, like, for all sets S, there exists a set T, and then you can follow by some kind of first order statement. But now you can talk about V being an element of S or of T. So you have these additional things. So that's what's called monadic second order. Existential monadic second order means that the quantification over the sets is existential. So the two examples we've had have been existential monadic second order. That is, that there exists a set S such that the set S has the property that it has the root, and for every vertex in it, there's a child which is in it. Okay.
Two nested existential quantifiers over sets at the start.
I count that. I allow that. Yeah, I allow that.
Over any finite number of sets.
Yeah, yeah. But I don't allow you asked sort of the hard, what happens when you start alternating quantifiers? But that's not, and that's a very good question, but here I just think of this. If you have a tree automata, you can create a monadic second order statement, but it's not unique. And if you think of the property of being infinite, if you look at that tree automata, one monadic second order statement is that the tree is infinite. The other monadic second order statement that also satisfies the tree that particular tree automata is the statement false. All right. That statement, remember we're saying that if you have any green children, you're green. So if you just say that everything's red, then it satisfies it. And that's the one that has probability 0. So where did this spurious solution 0 come from? Well, the tree automata really had given the automata, there were two monadic second order statements that reflected it. One had probability 0, which was this line, and the other was the other line. Okay. And then we have other connections. If we have a monadic second order, we can create a tree automata in a unique way, and from a tree automata we can create an existential monadic second order statement. And this we can do in a very cookbook way of looking at the tree automata, and then the tree automata, if we have green, yellow, and yellow, green, yellow, and red, the existential monadic second order is simply there exists green, there exists yellow, there exists red, that they partition all the vertices, so that's first order, and that for all V, and then the list of the properties we can write down. So we get this. What happens is that when you have a tree automata, you get an equation from it, but the problem is, or the interesting thing is, the equation may or may not have solutions. So let me end with some open questions. Yeah, question?
I give you the tree automata corresponding to an MSO formula.
Yeah.
Is it decidable whether it's whether it's representable in first order logic?
I don't know. I don't know. I can't decide it. I can say that. It's not decidable by me. All right. So let me end with some open questions. So you look at a tree automata, and you create this EMSO, this existential monadic second order, and from the existential monadic second order, you have this system of equations, and you look at the largest solution, and the question is that the probability of the event that you're doing? And I don't know. I don't know. Sometimes. Okay. And here's a question I particularly like. Let me back up to the equation. This is some reverse engineering. Let me go to my favorite picture here. Whoops, there it is. Okay. If you look at Draconian fecundity, if you look at the finite states, and then you're green and red, and you're green if and only if you have two green children, then one solution is this one, which is the one we want, which is that you want to know whether or not there's this complete binary tree. The other one is this one, which is the statement false, which is also there. And my reverse engineering question is, do you ever get this curve? That is, can you create a problem where the solution is this lower curve? I think not, but I'm not quite sure. I don't know.
Isn't that unstable?
Hmm?
If you did a perturbative analysis, you'd probably find it's unstable and unstable.
You're right, but I'm not sure that. Yes, well, I think that's an approach we're thinking about. Okay, I hope so.
Make a
All
point.
right, I'll work on it. Okay, good. So let me just go back and finish up. So yeah, can you get something where you get the smaller root? And I conjecture no, and maybe from the stability analysis one can show it. I'm not quite sure.
Not easy to create. I mean, you can do that, but it seems somewhat not easy to create properties where you get non-monotonicity in the lambda. I mean, you can do it artificially by saying,
Yeah.
you know, if
Yeah.
you have at least.
So one weaker, yeah.
It will be hard maybe
Yeah.
to create this shape.
Right. So one way of stating the question is, suppose you don't want to get the curve. Suppose you just fix a lambda bigger than the critical one, and now I just want for that lambda, I want a single statement that gives that value. All right. Well, now these arguments about stability maybe are not coming in, but I don't know. I mean, this is an interesting open question, and these general questions that really were what we started really from the beginning was to say, let's not look at Galton and Watson, the zero solution as some kind of anomaly. Let's say, let's look at that as a central thing. When do you get spurious solutions? Or to put it in another way, how do you know when you get this system of equations, which you can get, are there certain types of a tree automata? So first order generates it, but maybe some other things also generate, where the solutions are going to be unique. And then a similar question where you have corresponding properties, and the properties, we can't quite say the properties are unique, but unique up to probability 0. So that's a similar kind of question. So let me end with one of my favorite authors, Kundera, and I like this statement with exponentially well. So thank you very much. Yeah, Bobby.
Say I give you a tree automaton
Yeah.
with multiple fixed points,
Yeah.
and I pose the computational problem of deciding which of the fixed points is the
Actual probability.
probability.
Yeah. That's what I'd like to know.
Is that recursively decidable?
I don't. Yeah. I don't know. I don't know. I mean, it seems like, I mean, you should be able to distinguish between probability 0.3 and probability 0.7. I mean, if they're two different values.
Iterate it to sufficient depth and look at which one it's converging towards? Is that...
I'm a little bit worried. This thing of iterating is a little bit of a problem, you know, when... so let me maybe end with one example where funny things happen. Suppose you want that there exists a set S where every node has exactly one child. Okay. Now, if the tree is infinite, you could just take an infinite path. Okay. But if you look at the equations for that, then you would say that something is green if and only if it has exactly one green child. And when you do that, if you let x be the probability that it's green, then x would be the probability. So now it's Poisson lambda x children would have to be exactly 1. So you'd get this equation. This gives the wrong answer. This is actually just the wrong answer. The actual probability is known to be the probability that the tree is infinite, which is not that equation at all. I mean, everything's known about it. I mean, this has a solution, but it's just the wrong solution. So we don't really would like to understand, when do things work out well, when do things not work out? How can we find, if somebody's given, if you're given a monadic second order statement, how do you find out the probabilities? How do you distinguish which probability is the correct one? All of these are the questions we'd like to answer. The one place where we do know it is in the first order world, where everything is great. You get the equations. The equations have a single solution. Even computationally, it's a contraction, so you can actually even compute it quickly. Although the number of states is a tower function of k, so that's small problem if k is 10, but okay. But still, so in the first order world, we have a very good situation where we have a lot of knowledge. Once we go into the monadic second order world, where we've got a lot of open questions, we really don't understand it as well as we'd like to. Yeah.
Have you thought at all about enriching the language of trees to include, for example, Presburger arithmetic sentences about the number of children? So you could say things like, there's a node whose children all have more children than it has.
Yeah, that would be very good. I actually haven't thought about that particular one. One question that I didn't list on the open questions is to extend the first order system by adding ancestor. So it's still first order, but you have that x is an ancestor of y. So now you no longer have locality, because things can be far away. So that's, but I have no results. I mean, I wonder, you can ask all these questions, again, because it is monadic second order. See, ancestor is a second order. In the second order world, you can say ancestor because x is an ancestor of y if there's a path from x to y. So you can say that in second order. So that's the one. I haven't looked at Presburger, but there are a number of possibilities for between first order and second order. There are a number of things in between that are worthwhile to look at. Yeah, lots of questions. Okay, I know our host left, so I'll say thank you very much. Okay.